Jim Potty talk who just came now to listen to him, we switched. Okay, so there's a shift of three signal operations involved for having this kind of rearrangement. I also want to thank the organizers, although I've been an organizer myself. The others have done so much work, on the logarithmic scale was a slight difference. That's all. For having good time. That's okay. I would like to use the next 40 minutes to give basically an overview of what has been done recently in our labs with respect to multiphoton entanglement and how we use this kind of entanglement for performing quantum computations and quantum simulations. And what you see here basically is already some kind of idea what we like to do. We like to simulate some kind of all the nature, like aromaticity in benzene is indicated here, but I will come to that later. As you can guess from the talk, photonic systems are the systems that we like to deal with. Photons are a very nice level system because you can encode quantum information by using, for example, path degrees of freedom or polarization. We most often choose polarization. Series defined as, for example, horizontal polarization, orthogonal polarization. The vertical one is the one state, and you can nicely trace superpositions of those two states by taking, for example, the blob sphere, which is the Poincare sphere for photons, and you can change the polarization by using off-the-shelf elements like these phase retarders, half-wave plates, quarter-wave plates, with very high precision, up to 10 to minus 6, 10 to minus 8. You can really do by hand easily. You can also split the polarization. You can use this polarization-dependent beam splitters. The series state goes one path, the orthogonal polarization, one state goes the other path. It's a very nice system in that sense. And since the early days, since people figured out how you can actually generate entanglement between photons, it was a huge area of applications accessible to photons, and still the case. So since the early days, when now 10, 15 years ago, down conversion was the main material to generate photon pairs that entangle with polarization degrees of freedom. It was most often used for addressing fundamental questions. I guess all the first Bell tests with separated Alice and Bob and so on, and down with down conversions, many other fundamental tests. Of course, you can also use them as a quantum channel because you have entangled pairs, so you can take several down conversion sources. If you, for example, make some kind of linear operation here, you make a swapping and you can extend it even the distance, and you have this quantum channel over some longer distance than you would normally think you can do by just having one crystal. Of course, there are also natural choice for metrology. You can take single photons, you make path entangled states that all go this side or the other side, and if you achieve such path entangled states, you can improve the resolution of such a mirror better than what lasers can do, so you can go below the shot noise limit and look at the Heisenberg limit. And of course, the thing I'm interested in is this computation sector that was shown now more than 10 years ago that the measurement itself can induce an effective nonlinearity. Basically, you can see the single photons green, you have ancillar photons, you measure the single photons, you process your computation via such a circuit. So, the journey I have in mind is basically talking about some kind of engineering we have done to address scalability issues with down conversion sources. And then from the hardware section, we move to the software, which is more fun in my point of view. Talk about quantum networks, cloud computing, simulations, and then in the future, what you're currently working on, trying to improve technology and software. Okay, so what's important for linear optic quantum computing? The crucial thing is to have deterministic or at least heralded photon sources. So the key point is that since the measurement is done, since the measurement introduces the nonlinearity, we would like to know how many photons are involved. In other words, if you measure 5, if you have 10 photons, you measure 5, you basically process the other 5 photons, then you would like to know that the total number of photons involved. Okay, that's an important key issue for scalability. So what people typically draw in such kind of schemes that you have down conversion sources, the emission is random, so you basically kill and use one of the two photons here and here to trigger the event. You process the photons and then you make the switching and the gates by having additional detectors here to process the information. And the key point is you would like to have photons on demand to make such devices scalable. And moreover, it would be nice to have actually entangled pairs on demand for many applications, which I come now in a second to show. So a very nice gate to explain why heralded entanglement is important is the signal gate, which is probably the most important gates for two qubit gates for computing. In the polarization language, we take H and V as our 0 and 1 states. The if a control bit, you would like to have a gate, if the control bit is in a V state, then it flips the target gate. It's shown here. V becomes then H. And if you have such a device, of course, you can also generate entangled states. If you superpose the control bit, H and V, they can make belt states. And of course, other around, if you send belt states in, you can generate different outputs where you can distinguish what kind of belt state has been used. Nicely, it was shown that you just need, let me try to make this work, you just need two gates, two PBS gates to make a scalable CNOT operation. And the idea is that you just take two gates, two beam splitters, you stand in photons here, and if you have additional photons, like ancilla photons, that you can measure afterwards, and if they're entangled like that, and you superimpose the inputs and the input here with such an ancilla pair, then you can actually basically make a CNOT operation by making a measurement here and there. And if you know that one photon is here, one photon is there, then you know they have done, these two guys have done the CNOT operations counted at these ports. What's the key feature? The key feature is you would like to have photon pairs on demand, or heralded, that if you measure one guy here and one guy here, that you know there were actually 4 photons involved, that the others 2 here can go out without being measured and destroyed for consecutive gate operations. So it was actually an open challenge for a couple of years to make such heralded entangled pairs, and you could use down conversion, which intrinsically is actually random, because pairs we never know when they come out. But you could use quantum interference to at least herald such emissions of photon pairs. And the idea is that you basically build a black box, and randomly we get a trigger of four signals, like for light bulbs that show up. But if they show up, then we know there's 2 more photons involved, and these are in the highly entangled belt state. The idea was to use quantum interference to achieve that, and without going into too much details, because there's a computer science audience who doesn't care so much about the experimental stuff. Basically, we have a down conversion crystal pumped very hard, so we get actually 3 pairs at the same time. The tricky part is to split. If beam splitters see that 2 pairs go here, other 2 pairs go there, but the point is if you measure 2 pairs, 2 photons here, 2 photons there, then we know the others 2 which are left are highly entangled in the belt state. The tricky part is to split here as good as possible, that only 4 photons are on these areas and the others 2 go dead. And this can be done probabilistically, but the trade-off is you lose your total number of counts. So what's the takeaway message? The takeaway message is, yes, it works, but with a very low count rate. But the best we could achieve is we could prepare belt pairs of pretty high fidelity, 84. They could also violate CHSH inequality. That's the fingerprint always they have to do to confirm people, to show people that it's actually entangled. And here we could achieve different probabilities. So the highest probability was almost 80% certainty that we know there's a pair sitting, although it's not measured. The trade-off is, of course, the count rate. So we have to increase the transmittivity of beam splitters such that it's very unlikely that the 5th or 6th photon also turn around this way. So the total numbers are very low, but the price is for that they have very high certainty that the photon pairs there. And that's just important for scalability. Okay, it's enough hardware, so now comes the fun part. It's basically quantum software. And the third thing is like something like Elam already mentioned, and other people, the concept of blind computing, cloud computing, and so on. So for me, cloud computing was at the beginning something like that, where basically the supposition of cloud and sun and so on allows you to explain what's going to happen. But actually there's more fundamental questions below cloud computing. And the thing is that there was a question that goes back to 1978. So now you see the difference how experimentalists like myself explain blind computation, cloud computing, and how the computer scientists basically describe these methods. And you will see like the faces like, what is he saying? But the interesting part from me as an applicant, who just doesn't care so much about the details, is like there was an open question about safety, okay? And the safety was asked actually by Rebus 1978, so the year when I was born, asking, can we actually keep data encrypted all the time? Can we achieve that encrypted data is sent to a computer, processed and sent back, everything is totally safe, which is not the case these days, because when you have Gmail, cloud computing, Facebook itself definitely knows what kind of pictures you're having there, what kind of private messages you're writing. It's totally open. And the question was, can this be done? It seemed that this was a pretty tough question for mathematicians and computer science to find a solution to that, and I was impressed that it took 30 years to find answers. There were 2 answers that came up independently. One from the classical side, similar to classical quantum cryptography, who found a solution that has computational security, which means you're secure as long as the computer is not a quantum computer or strong enough that you can correct like factorization and so on within reasonable time. Independently, three people, one is here, Elham Kashefi, so it was M. Broadbent, Joe Fitzsimmons, and Elham Kashefi, who found an unconditional security model for this kind of encrypted data based on this one-way cluster state model, which basically was very interesting for us. So to say, well, that's interesting per se, and since we are in this cluster state business, we're very interested to do that. And the beginning of the experiment was more than 2 years ago in Elham's office. We had our first meeting there with the authors. We made the first drawings about what can be done in the lab. You can imagine it's like a huge gap of what computer scientists and theoreticians have in mind. But we said, no, this is all impossible. We have a few qubits, simple measurements. Then basically it was a long journey to find the same language. It took half a year basically to be on the same communication basis. And then during the course of the experiment, many interesting insights come up, but I will mention this later. So what they have shown is that you can actually make a marriage of quantum cryptography ideas and computation. If you put both together within this framework of measurement-based computation, then you can achieve that the client actually needs no computational power. It just has just needs the capability to prepare qubits with arbitrary phases. But he sends those qubits as input to the computer, who has the power. And the power means he's capable of entangling, making all those hardcore operations which are so hard to do in the laboratories. So the computer basically gets the qubits, makes the cluster state, makes the measurements, gets the result, and sends the answer back. So in short, he's totally blind. He doesn't know the input, he doesn't know the processing, he doesn't know the output. Okay? It's like a bad marriage, if you want so. Okay? So this guy has all the benefits, and this guy has all the work. So, in a nutshell, now, basically, again, experimental language, what people like us like to explain how security works. The idea is very nice because the cluster states allow you to separate what's classical and what's quantum in the computation. So, as you all know, the computation is defined with two parameters basically. One is the shape of the cluster. So you make this highly dependent cluster state. You measure like along one line, it's one dimensional, and you implement effectively this kind of rotations. So of course the shape is one parameter. One dimensional, one qubit operation. Two dimensional, you see two equal states, and you process your qubits along such a circuit. The other parameter is the measurement setting, because the setting itself defines how you teleport your qubit through the system. So if you hide now the shape, like if it's like this, or like this, or like that, and the measurement settings, nobody knows what's going to happen. So the point is, these classical parameters, which actually are part of the classical part, basically outsourced of the quantum part of the computer, if these are not known, then you can hide your computation. That's the idea of blind computing. So how do you hide the structure of the cluster? That's very nice and easy to understand. You find a generic subunit, so-called brickwork state, where each brickwork state can implement all the important ingredients you need for universal quantum computing. So you have this kind of, for example, 10 qubits. You choose particular measurement settings. You implement a Hadamard to this side, or pi/8 gate, or nothing, identity, or CNOT. Which means if you build your computer out of those brickworks, that's the reason why I guess it's called brickwork, no? Then you can get a snapshot of the circuitry. You have no idea what's going to happen, because just the measurement settings will define the computation at the very end. Okay? Which might be slightly different in circuits in some perspective, that you really can hide nicely the underlying structure. So that's easy, message is just build brickwork states and you're done. The circuit is hidden in terms of the shape. So now you have to hide the setting of the measurement, which is done by the computer. There's a little tricky part. So here's the indication that you don't actually need 10 qubits, you can use fewer qubits, 4 qubits, which we had in our lab, and we can also put them together to some kind of brickwork states in the big picture. So how to hide now the phase? That takes more than one slide to explain, but it's not very hard. The idea is now that in contrast to the regular computation, where you make a cluster state and all the underlying qubits are in a plus state, 0 plus 1, that's basically the standard case, we add this new phase here. Okay, and as we've shown, it just did 8 different settings. In other words, when you get the XY plane of the block sphere, you just did 8 different settings. You choose randomly, like here, theta 1, theta 2, theta 3, means like you choose here 8 different possible random settings randomly, then you have a new parameter in the system that allows you to hide the measurement settings. So in other words, the client prepares each qubit with a certain theta, only he knows. That's the only thing he's not sharing with the computer, and sends them to the computer who makes the entangling operations, the hard job. And the point is, the computer gets an entangled state, but it doesn't know its actual shape. So basically, similarly, you get a belt pair, but they don't know which kind of belt pair, 5 plus or 5 minus. That's similar here to the cluster states. So now he makes the measurements according to the cluster state rules. So he measures between the xy, so along the xy plane, which is defined by this parameter. But the point is, since he doesn't know the underlying phase for each qubit, he doesn't know what he's actually going to implement. So what you see here very nicely is that the computation proceeds. You take, in principle, a plus state and you rotate according to the measurement setting theta. But here we have this new parameter, okay? So actually, since he doesn't know the underlying qubit phase, he doesn't know what kind of actual rotation he's going to implement. Voila, he doesn't know what kind of identity or C0 he is doing. That's the point. So the protocol looks like just as before. The client prepares qubits, no computer power, sends with his random bit phases to the computer, he makes a cluster, he gets the order so to measure because the client knows the phases for each qubit. So he says, I know a phase, I know the rotation I like to do. I also add this kind of bit flip, that's important for error correction when you have this kind of clusters with no just details. So he makes the measurement here, and the measurement actually make the circuit, the computations the client wants, but this guy has no idea what he's doing. He gets results and sends it back to the. So with such an idea, we had such a concept. We had the challenge to implement this fine computation. Here you see the machine, the setup that we use. A down conversion source. A laser goes through twice, forwards and backwards. We get pairs in both directions. Here's the client side where we could choose thetas here on 1, 2, 3, 4 photons, which are not in the cluster state yet. They were sent to the server. We were just like a few centimeters away, but that was the setup experiment. So here basically the beam splitters that make the cluster state, and here the measurements done by the computer process, basically processing the computation. Of course, you can think that's just the setup in the laboratory, but there's no difference if you think of the global network, because it would be the same. You have photons traveling, no, not by mirrors, but by glass fibers, whatever you have in mind, all over the place. And then you have something like this that you can imagine, like here's the client, send something to whatever from Rome to Vienna, here's the computer, we get answers, don't know, have no idea what it means. Berlusconi is asking us to do, and then we can send stuff back here to Rome. But the nice thing here was that such a small 4-qubit computer, we could already implement a variety of different operations. We could really achieve in a blind fashion universal single qubit gates, non-trivial 2-qubit gates, entangling gates, could implement Deutsch algorithm, Grover's algorithm, and even make some little testing of the quantum services, cheating if his results are consistent with quantum mechanics, or slight probing, if he's cheating or not in that direction. As you can see, we had a bunch of measurements, so we're basically taking data for months. We have many settings, we got tons of measurement results, and we measured many hours. It's a really pure measurement time to get all those density matrices and characterizations, and we really measured our setup basically to depth to get results. So here, we like this story because it seems like there are two possible applications in the future. One is the obvious one. You have security that you can achieve for computing, because in the future there might be only a few computers available, and you would like to achieve that the client can keep this information secret, so the computer has no idea what's going to happen. And it seems that even in the near future, computers are very hard to build, so there might be only a few available at high facility laboratories, governments, universities, and so on. It might be an interesting technique. And the other thing is that you can also probe nature. You can see that this is a way to make computer blind or nature blind. You ask questions about complexity classes, about quantumness. This is really the result. You can hopefully can prove that the computer gives you quantum power, really due to quantumness, not by some other smart classical algorithm, but I come to that later. But the thing that we learned through the experiment, that actually I think half about it is our theoretician friends, we learned in the course of the experiment that the protocol is much more stable than we thought in the beginning. So what I mean by that, it means that if we have crappy results, the fidelity is not perfect, we have noise in the setup, the security is still established. Okay? So what you lose is the right results. The computation might be wrong, but by no means does the computer get any information about the thing you're trying to do. And that's a strong state. So it means that really security is the strongest umbrella, and anything else just means wrong results. The other thing is that's surprising for us, it's less demanding. So we didn't need to make all the 4 qubits fine. It was sufficient to just take 2 of them and randomly prepare the phases, because some computations, according to Clifford groups and whatever this kind of rules, actually is sufficient to make the computer blind. So in the big picture, it means you have a reduction in overhead and basically preparation costs to achieve total security by choosing smartly what kind of qubits you really make to apply this random phase. So these are 2 important messages which we have to thank some referee reports to actually address this one as well. But also in our discussions figure out, yes, real-life conditions in the laboratory actually provide insight into theory and the applicability of theories. And some side stuff, so this amount of measurements took some kind of investigation to how to analyze data and record, and now there's some spin-off now happening to characterize the stuff more properly. Okay, that was the quantum software for computers. Now we changed gears, we moved to a slightly different field, it's quantum simulation, which is a hype these days because it was shown that simulators are feasible because they don't need this kind of overhead as computers do. You don't need error correction, you don't need this kind of other methods which require tons of qubits. You can really have a few numbers and they already outperform classical counterparts. The idea is here stolen from a cartoon from Seth Lloyd, who shows the idea of a quantum simulator. It means the laboratory have access to a small quantum system. They have access to the parameters, so you can prepare your initial input state by some local operations or non-local operations to get a target state which basically mimics some complicated quantum system where you have no access to. The idea goes back to Richard Feynman, who was shown in the 80s that, of course, it's very hard to simulate a quantum system because of the Hilbert space and the superposition principles. We need an exponential number of equations to describe the situation of the system. Then he suggested to take a quantum system itself to reduce the cost of equations to mimic such quantum systems. And this idea was rephrased then by Seth Lloyd basically like 14 years later, who put this idea into the language of qubits and gates, and he could show that the number of qubits and gate operations just scales polynomially with the size of the quantum system, which is the speed and the benefit we get for quantum simulators. So this in mind, we like to simulate small systems. What are small systems? Chemistry. Okay? Because physicists always have this kind of infinite Heisenberg interactions and so on in mind, and here we could think of something smaller. And for example, when we take the simplest molecule, it's hydrogen, you have 2 electrons to make a bond, the singlet bond. Then of course they have to obey Fermi's rule. So the spins have to be different, a minus sign in here. We look at the quantum correlations, which are the hard things to calculate in a classic computer because you have to use approximations like density function theory, Harvey Fogg. If you do it like a correct way, like full CI, it's like takes crazy amount of memory and vectors and so on to get results. And here we mimicked this kind of idea of quantum correlations of electrons to the polarization correlations of photons. You see the entangled photon pairs that we get here from those cross sections have the same spin up, spin down, basically HV minus VH. You see that very similar. This we had in mind to actually get an access to those chemical bonds for the chemistry. So the thing that's interesting when you go to the simulation of these pairs, there are basically 2 leagues. When you talk to physicists, they say, well, valence bond states. That's the way to think. Valence bonds means it's the highest occupied bonds, and there are 2 systems out there. Either the case when they're localized and they're pinned down, so they don't hop. They're like sitting on lattices and they're really not moving. Or you have the opposite case, that they're flexible, they basically can resonate. You can hop around, delocalized, like a spin liquid configuration. And it's interesting for the community because the transition from here, like localized to delocalized, suggested to be a mechanism for these superconducting ITCs. Because people think that when they cool down, they move from here to that stage, and that it's interesting to take a closer look what quantum physics can teach you and tell you what kind of secrets are in there. Chemists have something similar in mind. They have smaller systems. So, for example, that benzene, it's a carbon, 6 carbon like a ring. Each carbon is 4 electrons, they're like, but only 3 neighbors. No, there's a hydrogen, carbon here, carbon there. So this guy has only 1 extra electron. So does the others. And of course, they may also make a bond. So they have now 2 options to make a bond to the left side or to the right side. They can hop around, so they're also delocalized, this aromaticity. And depending on the temperature, they're either delocalized, they hop around. When they cool down to, let's say, 70 Kelvin, then they're like pinned down, similar to this configuration here. We wanted to simulate such a hopping of the bonds. So the easiest thing we had in mind was to, well, of course, we tried the simplest case in the beginning. So we took 4 qubits, crossed with half particles. We have 2 bonds like this or like that, and we were interested in moving them around to see if you can learn something from quantum physics about the configurations. So we write it down properly in a Hamiltonian, which decides as interaction for 1, 3, 2, 4, and then interaction strength J2 for the other ones. So we basically change the couplings for different spins. So that's the idea what we have done. We started with 2 pairs. We changed the interaction strength, this Heisenberg interaction. I didn't mention, everything is like within the Heisenberg picture. We have basically XX, Y, C coupling. We changed here the interaction between those pairs by having some tunable parameter which allowed us to have different coupling ratios for the different spin configuration. That's in a nutshell the picture. 2 down conversion sources, 2 pairs, and here you have this interaction that allows to simulate different interactions of the spins. And in such a setup, we had actually access to these different parameter regimes. We could simulate the valence bond states, as well as those superposition states, the liquid states, who are either according to the S-wave pairing with the plus sign, the famous D-wave pairing for superconductors with a minus sign here, and things that we could simulate. And here you can actually see how we could move around from this configuration to that and so on. So that's the setup, as I just shown before. The new tool we had here for making this complicated simulation was the tunable beam splitter that's shown here. So the point is we have a single pair here, another single pair here, this Heisenberg pair from the very beginning, coming from the down conversion. It's nice, we get it for free. Here we had a Heisenberg interaction, because by forcing ourselves to look at different output ports, we looked at the antisymmetric state of photons. I'll come to that in a second. We could tune here our simulator by having basically 2 fibers. If they're far away, then the photons just travel along the line, like here. If they're far away, they're shown here. Separation of the fiber versus what's happened to the photons, if it's transmitted or reflected. Fibers are far away, photon stays in the path. If they get closer, they're bare fibers, so there's an evanescent photon coupling. There's a tendency that the photons pop to this side, and if they're really very close to fibers, like here, basically on top of each other, you have 100% hopping from this fiber to that fiber, and that was our tool to simulate the ground state properties of this Heisenberg interaction. Another thing that already Martin mentioned today, that ground states are important for simulators. You would like to start very often in ground states. And we could really force ourselves to stay in a spin zero ground state due to this interference effect here, that we stay always in a spin zero subspace, as well as preparing our states here for the down conversion. Okay, that's the details of the beam splitter. Only photons that are in the so-called singlet state that are antiferromagnetic, so antisymmetric, according to this equation here, a minus sign to hop out to the different output parts. And this is done normally in the lab by characterizing the beam splitter. So we have a source sending our singlet state, and if they overlap perfectly the beam splitter, you see an enhancement in the coincidences here, the output ports, which is shown here in this curve, that when you're at this spot, then you know you're precisely at the right spot for doing such a simulation. So we did, again, plenty of measurements. We had many events to register. We had pretty high fidelity. And the nice thing is we could now extract the density matrices for different configurations. So we could really get a fingerprint of each configuration. That's shown here, like superposition states, liquid states, so like solid states. Of course, if you have Hamiltonian, you get eigenvalues as well, the energy. So we compared the energy that's out there theoretically with our measurement results. They're pretty close. But then you could ask, so why the hell are you doing this? What's the point that you can learn of this simulation? What was the message here? And the message was, in the laboratory you suddenly have access to quantum phenomena. You can really use quantum information methods and techniques to get insights. Why is nature having this kind of mechanism? Why is frustration arising up naturally? And the point is that we could zoom in, we could really look at each photon talking to the neighbor and get basically an idea of what's happening when you have different parameter regimes. And the point is that we looked at the Heisenberg interaction between each photon pair, that's basically this equation. We could learn there's a very strong constraint, this kind of monogamy in the system, which allows us to explain why the photons have no other way than hopping around in the superposition states to obey this quantum monogamy, which means that the total amount of energy in the system basically cannot be increased. So there's just two entangling pairs in the system, no matter what you do. So if you change parameters, frustration arises naturally, and that's a very nice alternative approach to get ideas why physics is happening as it does, just from very fundamental quantum information aspects. This said, basically the message of the simulation was just this curve which shows the monogamy relation. So here you see the change of the beam splitter, the interaction between the pairs, and here you see the energy for individual couplings, pairs. For example, we start with this coupling here, you see it's very high, they have the highest energy. We turn on the interaction, so we go this way. And you see how the interaction strength, the energy between these pairs is decreased. But at the same time, in new configuration, this coupling comes up, okay? So you see here's a degenerate case, they're like both in a superposition state. If you change again the beam splitter effectivity, you end up in this configuration, you continue interaction, so you decrease again, you see that suddenly another configuration shows up. So the point is that the total energy is here, but the entanglement stays the same in the setup, but you see monogamy relation forces you have this kind of weird configurations. And I think it was very nice to see like a toolbox experiment that quantum physics allows you to explain complicated solid state phenomena. So the question is, can you blow this up? Can you go to real interesting cases and say the thermodynamical limit? And the answer is yes. You don't need much to do for that. Just have to increase additional couplings like this, also between next nearest neighbors, which means some more beam splitters. If you add just one more pair, like a 6 qubit case, then you end up in 4 different ground state configurations. The point is they are actually already generic for the thermodynamical limit. So actually this one allows you to get insights about the ground state properties of much bigger systems. And as you can imagine, we have something like that in mind pretty soon. So if that I come to the last minutes, I guess, we'll just rush through what we're doing these days, what we're like working on, kind of challenges we are facing. So on the quantum hardware side, we're of course trying to improve our systems such that we get more photons, more qubits. And the idea is to have some very good photon source, with very nice circuitry and everything here is detected, ideally on the chip altogether. And the different groups having different approaches to realize that. So we are very optimistic that in a few years from now we have 10, 12 photons and we can use polarization and paths. We have more than 20 qubits on the table, so I'm really optimistic about this development. So we work of course on photon sources to improve the efficiency in this regular down conversion process. That's our expertise in Vienna. We follow the main trend that many groups these days do with waveguides. There's the Bristol group and the Italian groups with Milano and Rome, and then there's of course Australia and many others who use waveguides which allow you to make the circuitry smaller and very stable. That's something that you also do in cooperation with the group in Jena, and we follow the idea of using laser-written circuits where you can really make 3D structures and so on. But the main feature that we focus these days to improve collection efficiency. So we lose many photons by just having bad detectors. Bad detectors, I mean, they have efficiency of 30 to 40%. Now we're using superconducting nanowire detectors, collaboration at MIT, where we have nanowires so very fast. We need fast recovery times because of pulse data systems. The only things on the market are basically those detectors. So for purchasing such and developing such a system, we acknowledge very much the support we got from our friends, because I'm already here. And basically we are looking forward to the next years to have a few of them to boost our boundaries. But that's the hardware side. So we're all interested in quantum software. What can we do in the meantime to learn about quantum physics in this computation and simulation direction? And there's one big question out there, like how much quantum actually is needed to do quantum information? Okay? How much quantum is needed to have enhancement in this processing? And by looking, for example, at different measures, you know, there's a slew of parameters you can choose. You can choose entanglement information, you can choose tangle, you can have bending qualities, you can have quantum discrepancy. All these curves have slightly different behavior. So what you see here is the mixedness basically of the state, like mixed state, by the entangled state, and here's the parameter that you use, like discord is high or like tangle is high and so on. We wanted to know, can we actually get some ideas what kind of parameter fits better or which one is less appropriate? And by doing this investigation, we learned from Chastov's team that discord is actually a very highly discussed topic these days and has very interesting aspects. And they've shown that you can actually map discord to some kind of remote state operation protocol, which was interesting for us to make an experiment. And here's in a nutshell what happens. So we could show that Discord allows you nicely to explain when you make a measurement here how good you can prepare remotely on the other side a state. So we just had to build a photon source, like a simpler one, 2 photon source. Had entanglement here. We took different states and measured the fidelity of the remote state preparation using Discord. And the point here is, which was actually very surprising for us, was you find a very nice situation where you have states with no entanglement of Discord that outperform entangled states. So in other words, this guy here has no tangle, but he has Discord, and does something better than this guy here, who has entanglement but lower Discord. So you see there's a separation. What we tried here is to make remote separations for different spheres, and this is real data we've taken. This is just regular oscillations because this experimental world is slightly tilted, but it's like 99% fidelity, so really, really good numbers actually. Here you can see that there's sometimes there are interesting measures that catches something that a well-known measure like entanglement does not catch. So it was interesting to think about this stuff, and hopefully we have to do something in the future along this line. In the bigger picture, there's also a question, well, there's communication purposes, but what about computation? Can we also ask questions about how good is a quantum computer in terms of quantumness? Does it need quantum powers and so on? And here we follow definitely in the future the idea of the blind computation, where now the first step we made a blind Bell test. Okay, so it's this first step towards verification of these quantum computers. We made a Bell test that we have basically a computer as a box, where the general question is there quantum involved or not? Or in classes like PQP, like belong the computational class versus PPP, and you can please ask Alan for details because I'm just a experimentalist doing the stuff in the lab. But the idea that we've had here is like to get an input unknown to the computer. That's a blind quantum computer now. Basically makes a Bell pair, it makes the measurements, and it gets basically a violation of CHSH without knowing that. Okay? That's our first attempt to probe quantum computers if we really, that we can be sure that there's quantum power involved with processing data, not some smart underlying classical algorithm. Can we have this in mind to take a closer look in the near future. So probing nature basically. We also have in mind to implement algorithms that's more like along the circuit model. And here nicely you see how theoreticians basically make your life very hard. So suddenly ideas come how the algorithm can be implemented. So you have this kind of printouts and you have this kind of tons of gates, and then you start discussions, Blackboard discussions. Actually, what's a feasible case to implement in the laboratory? Then you have boards and you see circuits and CNOTs and blah blah. Then you see this kind of stuff, and the theoreticians say, well, we just need a few CNOTs like this, and then you say, well, yeah, we try, and then you see the few CNOTs on the board just correspond to half a lab. Okay, so we're now building a lab, basically half the room. First CNOT, as I've shown before, where we can actually feed forward our results. Second CNOT here with such a device, which A shows that in the future we'd like to shrink everything on a chip just for the lab space. It's like a really painful thing to arrange such things. We would like to move to waveguides, and we hope with such a device that we have now in the lab we can address different algorithms. For example, we have something happening here, discussed with friends in Harvard and MIT about this self-taught algorithm, as well as our local friends, Frank Lestratis group, that we can actually implement some kind of cooling algorithm, this metropolis algorithm, to get ground states. Of course, we have discussions with our friends for simulations. I'm a chemist in background, so I like to simulate chemistry. That's something which is out there as well. And in the future, I'd like to combine gate operations and simple waveguide structures, such that we can simulate also other crazy particles, like particle physics. You know, you have basically here six qubits. You can think of having spin degrees and flavor degrees of freedom. With changing parameters here, you can simulate protons, neutrons, or Dirac delta particles, and that's something which we would like to do in the laboratory as well, just to get an idea about quantum physics that might be inaccessible otherwise, to see the phenomena on the table. And the thing that we have just finished is like a XY Hamiltonian simulation where we had a setup like this. One CNOT was put into the source, another CNOT was here with such two CNOTs and local operations. We could mimic external fields, magnetic fields for some XY Hamiltonian. We could simulate a phase transition, which is just the teaser shown here, different eigenstates, 1, 2, 3, 4. You see the change in the phase transition here, the change magnetic field, which corresponds to a change of local parameters. So that's also nice to show that photons indeed allow to get a nice, meaningful tool to simulate solid-state physics hard-tech physics or chemistry. With that, I reached the last slide. We're also interested in addressing scalability. Scalability means you have to make deterministic gate operations, and here we use our Viennese strong environment with atom experts. There's on one side we have this cavity QED experiments in Arno Rauschenbeuten, where he has evanescent light fields, basically from a fiber where atoms sit. We would like to feed in single photons to make them talk to atoms. We make a deterministic gate. That's the idea. That's some one project that we have. Second project, if Michael Trubke, who's sitting in the third row, is to use new sources based on nitrogen vacancy centers for single photons and of course multiphotons. They're just very nice and can be coupled nicely to waveguides. There's some project which we started this year in France and Nottingham through BEC experimentalist, where we map photonic states onto the BEC, which is sitting on a chip. So we are the photon guys making the tailored photon states and tangled photon states. We would like to A, get inside what's happening in the BEC, and B, to manipulate the BEC by making appropriate measurements on that one photon guy, which is a link to the other photon that's basically linked again to the BEC. With that, I would like to thank the main people who did actually the work. So just showing off with things I've not done. And this is the group, Stephanie in particular for the blind computation, Max is with the waveguides, and basically for the gates it's like Martin and all dealing with that. And so other people working with either sources or papers. Okay, with that I can wrap up my talk. So I've shown that we work on the quantum control section to improve sources. We deal with this software part about with computations to make hopefully cloud computing possible some couple of years from now. Simulation is a main topic for us because we're interested in studying quantum physics of other systems. This is the long avenue we have to face in the future to improve numbers of photons, better control, which hopefully allows us to make other simulations, more computations. And with that, I thank you for your attention and reach the end, hopefully on time.
Questions?
Or the sleeping.
I have a question. It's maybe for Johan. So you have this universal graph state, and you decompose it into a 4-qubit graph.
We just have 4 qubits. For this case, we just prepared 4 qubits in a graph state.
Yes, but in the decomposition, what are the connections between the pieces of graph? I mean, there are some yellow pages in your picture.
Oh no, we just in principle we can link them. So we just prepared subunits of 4. Okay, and the color means that we can think this as a subunit of the bigger brickwork stick. So it's just like for the eye to guide you, but there's no physical meaning.
Okay.
You mean this one here?
Yeah, this one.
Developed connected. So we just work with structures like this, 4 shaped like this, or 4 like this, and so on. Just so that they can be seen as sub-elements of the brickwork state. So we learn from any of the others, it makes no difference if you have the full brickwork or just the smaller subunit, because the smaller subunits in principle allow you to build up the bigger one.
Okay.
So we were happy about that, otherwise we would have to struggle a lot to go up to 10 qubits. It's a reasonable time. Sure?
So in your quantum simulation experiments, you are simulating relatively small systems, which I suppose you would have been able to simulate on a classical computer. Yes. But I think there is a recent paper by Viv Camden where she tries to describe a very small quantum physical system, some kind of a quantum cellular automata, where she says that small number of cells and dimension and a bit of noise, this will be already out of reach for a classical computer to simulate. So I was wondering how far you are from being able to quantum simulate stuff that a classical computer cannot simulate.
So they asked the $1 million question. The final number seems it's around 20 qubits. So there are complicated, there's a computation hard problems out there where photons are feasible, like random walks and waveguides and so on, where a number on the order of 20 can outperform 25 and outperform a conventional machine. So of course we're looking for what's the simplest case where the first time in the world it can actually really outperform a conventional machine. And I'm very optimistic that in a couple of years from now we might do definitely the first outperformance. If it's interesting, this problem, that's another question. But I think in a couple of years this can be done. Less than 10 for sure. It's not promise. Judge me afterward.
Other question?
It's a $2 million question. Ion trappers claim to have 10 entangled diodes. So suppose they have 20 and you have 20. What would be your advantage against the ion trappers?
The same advantage as we have now. So there's things we can do better. Some gates we prefer to do. Some gates they know to do better. So Marcus is here to basically comment on that problem as well. The other thing in photons is I like this kind of random walks. So when I like the idea of studying phenomena that are based on pure random walks, the photons are a natural choice to do so because they just propagate freely. As you know, there are actually interesting questions out there where you don't need an actual circuit between the photons. So like you have a product state, you send it through a complex random walk circuitry, you can simulate the permanent matrix, for example. And this, they don't need actually many photons to outperform a conventional machine. And the ions also do random walks, but for them it's not as easy as for us to do because it just means do nothing. Yeah? Just make the photon, let them follow the normal propagation. So I'm very lucky that there are differences and I hope in the future we still have our own benefits, but they can do better than us, but it's a big Hilbert space with many different applications and so on.
So let's thank Philippe again.
Thanks.